In this video, we're going to talk about the regression line. So we're interested in linear relationships with the data, and ultimately, that's useful if we can actually create an equation of the line that we could use to predict the data and approximate the data. So we call that line the least squares regression line. And the equation for the least squares regression line is y hat, that's how we pronounce that, y hat equals a plus bx. And the formula is actually a little bit complicated. So first, x bar and y bar are the means of the x values and the y values. Means of x values, and this is the mean, not means, sorry, just single mean. And this is the mean of the y values. Okay, so the equation for finding A and B, the equation for A is to take the mean of the y values and subtract the B, which we'll talk about how to find in a second, and times that by the mean of the x values. Okay, so to find B, that's a whole other beast. B for beast. Okay, so you would find the sum of every x data value and subtract the x mean. And then you do the same for the y values, subtract the y mean. You'll multiply them together, add them up, and then divide by the sum of all the x values minus the mean squared. Yikes. We're not going to do that. Okay, we're going to go ahead and use either Excel or Google Sheets to find the least squares regression line. Lucky you. All right, so we actually looked at this example last time in the last video when we talked about graphing using a scatter diagram. So I'm going to go ahead and continue using this data, and I want to find the least squares regression line. So I'm going to do that on both Excel and Google Sheets. So let's start with Excel. Okay, so here was my scatter diagram. I'm not going to get rid of it because there is a way to find the equation of the line right off here. Okay, see right here where it says trend line. So first of all, I'm going to click that. And then let's see, linear. Yep, that's definitely what we want. And there should be a way to ask to see the trend line. So let me see if I can find that. Nope, I want linear. Oh, okay. Display equation on chart. So clicking that, and there it is. It's hard to see, but that's the equation. That is the A and the B. Now, so negative 0.0029 plus 0.8861. All right, let me write that down. Was y hat equals negative 0.0029x plus 0.8861. Hopefully I wrote that correct. Notice I called it y hat, even though Excel didn't. I'm going to, because that's how we refer to the least squares regression line. They did put it backwards compared to how the book has their formula written. They have it with the A first and then BX, or the y-intercept and the slope in reverse, but it really doesn't matter. It's the same equation. Now, let's go ahead and talk about what this line tells us. So let's interpret the slope and the y-intercept of this line based on understanding the data. So remember, this data was talking about how many colas a woman consumes per week and what her bone mineral density is. So the lower the bone mineral density, the more brittle the bones are. So that's not good. All right. So let's interpret the slope. So I noticed, first of all, the slope is negative. So that would mean that as you're consuming more colas, the bone mineral density is decreasing by that amount. Okay, so that's how we interpret the slope. As you consume one additional cola per week, the bone mineral density decreases by 0.0029. And what was the measurement? Grams per centimeter squared. I'm going to use all the terminology they did. And there you go. That's what happens. So as you place higher and higher X values, the bigger and bigger you're subtracting those values from the bone mineral density. Okay, so the y-intercept serves as kind of like a starting point. When X equals 0, that's when we get our y-intercept. So if you consume 0 colas per week, then you can expect a bone mineral density of 0.8861 grams per centimeter squared. And you may want to even say on average a bone mineral density of 0.8861 grams per centimeter squared. And it could be higher than that, but that's just based on this data that they gave us and based on the colas consumed. So the two people with 0 were a little bit higher. Well, there was actually kind of between those two values. So yeah, it's kind of took a little bit of an average between those values. All right, so let's use the least squares regression line to predict what the bone mineral density would be. And then I'm going to show you how to do the least squares regression line on Google Sheets. Okay, so to make a prediction, we're interested in finding out 10 colas per week, what that's going to give us, which was not data measured, right? So we're using this to actually make a prediction. So that means I'm going to plug 10 in for X. Times 10 plus 0.8861. All right, so I'm going to plug that into my calculator because I did not have this ready. That's fine. My dog is sighing at me because she can't believe I didn't have it ready. There we go. I'm getting 0.8571. All right. Grams per centimeter squared. I'm just going to keep tagging on that little label. So that's what I'm predicting. Pretty terrible in comparison to even the lowest here. Okay. So that's what we're predicting with this line. Now, I am going to show you how to do this on Google Sheets. And I believe there's one more part of this problem. Yeah, so there's more to this, but I'll get to that in just a second. So let's go ahead and work on Google Sheets. And I should still have the data there from earlier. Yay, I did. Okay, so this should be similar. I should also be able to keep it on this graph, have a way of finding the trend line. So let's go ahead and scroll. I think it's under series. Let's see. Oh my goodness, I can't believe I remember. So under series right here, trend line. Boom, there it is. Okay. And I think I have to, yep, label, use equation. And there's the trend line right up here. Okay. Now, I'm super happy I showed you this in both Excel and Google Sheets, right? The trend line they're using, notice they're using scientific notation. When they say negative 2.89 E to the negative 0.3, that's scientific notation. That's using negative 2.89 times 10 to the negative 3. So that means you move the decimal 3 places to the left. So here, let me just write that down. So hopefully that makes sense. Oops. And scroll back. Okay. So they wrote their equation in the form negative 2.9 times 10 to the negative 3. And in scientific notation, that means, you take the decimal point on that 2.9 and you move it 3 places to the left. And then because we're moving it, we're going to have to add 2 zeros in front. And that happens to be that number right there. So just be aware if they give you scientific notation, that's how you get it out of scientific notation. Okay, now there is some other important information we can get from both Excel and Google Sheets. And it has to do with how we know the strength of a linear relationship. And that's using this thing called the linear correlation coefficient. Okay, so the linear correlation coefficient has some important properties we're going to talk about, but let me show you the formula of it first. Now, you might remember earlier when I showed you the formula for the least squares regression line, the formula for R is so much worse. Yikes. Okay, here we go. So R, that's what we use to represent the linear correlation coefficient, equals N, which is the sample size, times the sum of all of the X and Y values multiplied and added together, subtracting, adding up all of the X values, timesing it by adding up all the Y values, divided by the square root of N times the sum of all the X values squared minus the sum of the X values and then squared, and then doing the same thing for the Y values. So N times the sum of the Y values squared, summing the Y values and then squaring it. Yikes. Oh my goodness, that's terrible. Here's what it does do for us. It shows us the strength and the direction of the linear relationship. So it shows strength, and I'll explain that in just a second, but the direction it shows by whether it's positive or negative, meaning positive association, negative association, meaning increasing, decreasing, meaning positive slope, negative slope. All right. So the sign of R indicates that whether or not we're talking about a negative relationship or a positive relationship. The strength we're going to talk about when we talk about the properties of the linear correlation coefficient. Okay, so the linear correlation coefficient R is always between 1 and -1. So it never exceeds those values. So the closer it is to 1 or -1, the stronger the linear relationship. So the closer R is to 1, the stronger the positive linear relationship. And similarly, the closer it is to -1, oops, that's not how you spell close. Close to -1 means a strong negative linear relationship. And I'm going to abbreviate that. Okay. When it's close to 0, or even stronger, if it actually equals 0, that means that there's no linear correlation. So this means no linear correlation. So if it's close to 0, we have a weak linear relationship. If it equals 1, it could equal 1. If it equals 1, that means it's a perfect positive linear relationship, meaning they line up perfectly. Every point lines up exactly on the least squares regression line. And similarly for -1, it would just be a negative linear relationship. So it's all the same, perfect, negative linear relationship. All right. Those little symbols mean repeat what was above. Okay. And as I mentioned, when it's positive, that tells us that it's the negative relationship. When it's negative, it tells, when it's positive, it tells us a positive relationship. When it's negative, it's a negative relationship. And I'm indicating the direction with which the data goes, whether it's going increasing like that or decreasing like this. Okay. So we can find this from Google Sheets and Excel. I will show you both. One of them is more straightforward than the other, okay? And one of them alludes to the next topic. So I think it's Google Sheets that isn't as straightforward. So I think I'm going to start with Excel. I'll show you how to find R on Excel. Okay, so here we go. Same general area here. Yeah, we're formatting the trend line. Okay, yeah, come over here. More options. So no, I don't need these. That's not what I'm after. Sorry. Let me see if I can find it. Let me need to grab my keyboard here. All right. So if I maybe it's this arrow here. No, that's what I clicked earlier. Okay, here we go. This is what I was looking for. Okay, so I said to display the equation on the chart, but here's the one I want you to see. Display R squared value. Oh, actually both Google Sheets and Excel do the same thing. So this R squared is the R we were just talking about, but squared. Okay, so R squared equals 0.6491. Let me come back to my page here. 0.6491. Hold on, sorry. I forgot it the minute I left. Yeah, 0.6491. All right. Let me go ahead and write that down. So R squared equals 0.6491. Now, real quick, I want to show you on Google Sheets. It should be same general area of where we set up the trend line series. Trend line, show R squared. Okay, so same thing. There's R squared right here over next to the trend line. R squared equals 0.649. So same value, a little bit less. All right, what it is it's literally this R that we're talking up here squared. So if I want to find little r, I need to take the square root of that value. So grab your calculators and take the square root of 0.6491. All right, I am getting 0.80. I'll just round to 6, 0.806. I mean, I could have done 5.6, or actually 5.7 if I was rounding. Okay, now the question is my value positive or negative? And that depends on my linear relationship. So up here, when I had graphed it, all the way back in the last section, I had that graph there. It's negative linear relationship. That's also reflected in the least squares regression line we found, which had a negative slope here. Okay, stop moving. There we go. Negative slope. So our R value is negative for this example because we're looking at a negative relationship. So this would be the R value. And based on this, well, it's certainly closer to -1 than it is to 0. So it has a relatively strong negative linear relationship. So I would say, we'll say moderate to strong. Negative linear relationship. I mean, I may even just say strong, but it was the scatter diagram that makes me want to say moderate to strong, because the scatter diagram, I felt like it could have been a better grouping. Okay, so that's what that value tells us about our least squares regression line and how good of a job it's going to do predicting the data. That's what this is telling me. All right. Now let me explain what R squared is, but before I do that, I want to go ahead and try another example here. So we're going to look at a random sample of 11 statistics students, and we're going to produce a least squared regression line from that. And we're going to do something called a residual. So let me talk about what that is first. Okay, so, oh wait, sorry, we're X's and Y's. So can you predict the final exam score if you know the third exam score? Oh, okay. I guess they're just wanting to know if there is a relative linear relationship on this. So there's a couple ways to do that. We can compare, we can go ahead and enter the data and look at R and kind of see how strong of a linear relationship there is. And if there is a stronger linear relationship, that would mean that, yeah, you could use the third score to predict the final exam score. Okay, so let's do that. I'm going to go into Excel to do this. And unfortunately, I can't grab the data like I cheated last time and did. Let me go ahead and just grab a new sheet though. Thank you. Close off. All right, so I'm going to go ahead and type it in. So these were the third scores, and this was the final exam. Okay, so it was 65, 67, 71, 71, 66, 75, 67, 70, 71, 69, and again. Okay, and then the final exams, which were out of larger values, so 175, 133, 185, 163, 126, 198, wow, 153, 63, 159, 151, and 159. Okay, there we go. So let's go ahead and look at the relationship between these two. So I'm going to go ahead and I'm going to start with the scatter diagram again. And go ahead and look at the trend line. Oops, for that, please. And I'd like to know, there we go, R squared. Okay, so I'm going to take, oops, that R squared value. Oops, stop it. And I'm going to plug it into the calculator and I'm going to figure out what the square root of it is. So the square root of 0.4397 is 0.66. That would be R. Because this is going in an increasing direction, the line is increasing, it would be a positive R value. All right, so let me go back to my notes here. I'm going to write that down. So based on that information, I'm getting an R value of 0.66. Now this is definitely not as strong even as my last one. And based on the graph, it really wasn't even all that great of a relationship, but it's certainly not what you would call a weak linear relationship. So I would say you could predict it. You can predict it, but I don't think it's going to be that accurate. But it won't be very accurate. Because I would definitely categorize this as a moderate linear relationship. So this would be a moderate, positive, linear relationship. And I'm going to abbreviate relationship there, REL, period. So yeah, I don't believe this would be very accurate. Okay, so residuals. This is what I thought they were actually asking us for. The residual is the difference between the observed value of data and the predicted value. As a formula, we could write that it would be y, which is the observed value, minus y hat, where we're referring to the prediction given by the least squares regression line. Okay. So using our problem earlier with the colas, let's find a residual for 10 colas. Actually, that doesn't make sense because 10 wasn't data that was actually collected. So let's do a residual for 8 colas. I'm going to make an on-the-spot change here for 8 colas. So, oops, based on the data, 8 colas is 0.865. So 0.865 here, changing this to 8. Okay, so the least squares regression line was negative 0.0029x plus zero point 0.8. I think it was here. Sorry, I have to look back at it. 8861. There we go. 8861. All right. Okay, so we're using this to predict 8 colas. I'm getting 0.8629. And now I'm going to compare that to what was actually recorded in the data. And I'm going to find the residual. And the residual is going to be the actual data minus the predicted data. 8629. Okay. And that gives me 0.0021 difference. Not too bad. Pretty close. Oops, but that would be the residual for that specific data value. That's how far off it was, the prediction from what the actual data value was. All right, so the last little piece of the least squares regression line is what's called the coefficient of determination. And the coefficient of determination represents the percent of variation. So it's a percentage, and it's r squared. In fact, it's the same r squared that we got off of Google Sheets and Excel. That is the coefficient of determination. So in our bone mineral density study, we got an r squared of 0.6491. So that is a percent, 60, let's just say 65%. So here's what that means. That's the percent of accuracy of the least squares regression line. So we can expect the least squares regression line, and they do often abbreviate least squares regression line, LSRL, least squares regression line, just because they get tired of writing it. To be accurate, oops, that's not how you spell accurate. There's not 2 R's. To be accurate 65% of the time. But what it really means is that's how good the colas predict bone mineral density, because that's what we're really measuring, what the colas do in terms of the bone mineral density. There's a 65% correlation between them, or relationship between them. So we can think of that as how accurate the colas per week are actually predicting the bone mineral density. But we are using the least squared regression line to do that. So it's not incorrect to kind of think of that as the accuracy of the least squared regression line.